All right. This is our second online DSP lecture. Again, I'm out of time at a conference. Sorry about that. So thank you. Appreciate it. You who are here, I can see your name online, so we can have some interesting discussions on this topic. I will also record this lecture so you can review when I post it or your classmates and I send out email, they can review at that time. So let me start it by saying that today I'm trying to use some interactive tools to do, and then I find it's very difficult for me to show you real examples, numerical example of C transform. So I think I will probably just leave that to next week when I'm back to the classroom. It will be much easier for me to work on the board and I can look into your eyes and communicate with you. So today I'm going over with the rest of C transform, showing you some MATLAB examples, and then I will start the part on Fourier transform, Fourier analysis. Some of the slides, so I think it will be easy for me just to show you online. And on Friday, please wait for my message. On Friday morning, I may have a conflict here, time conflict at a conference. If I cannot make it on real time, I will make a record. Or when I get back to Baylor, I'll make up the time for the class. All right, so let me share my slides of the Z transform. So here we go. So we have just do some quick review on here. Let's do this. So just some quick review. What we had last time is we are doing an inverse E transform. Inverse E transform, we have used a method from the textbook, which is doing xz divided by z. And then we are trying to find a familiar format. Then we can do a lookup table. For example, I have this is a single pole like this. It will be very easy for me to do inverse E transform. The pole is just the root, and I can put in the time domain. If it's double pole, we can also do a lookup table. It is npn like this, and we can put it into a lookup table and find the time domain. Then we mentioned that actually the first order, second order on the denominator is the worst case we can face, right? If it's more, you can always divide it into smaller orders because my parameters A's and the B's, they are real. If they are real, either I have real pole or I have complex pole, but they are complex conjugate pairs. So they are just two, the most. And then we find some way to analyze LTI system. Now we have this strong tool. We can do a forward Z transform, bring that into the Z domain. What is the reason we like to do that? One of I guess, the strong reason is that because convolution becomes a product, right? Just remember that convolution in a transformation domain becomes a product. So it's easy to calculate. And we can easily find the division to find my H, which is the system response. And then we can do an inverse transform. Now we know that. In that way, we can uniquely identify the system giving the input and output. So that's something we like to do. And then we analyze the Z transform, analyze the LTI system in the Z transform. We have looking to if a single pole, single pole like this, we know this is the transient response caused by the feedback of my system. And then I have a steady state, which is the pose of the input signal. So it's determined by capital XZ. So we have, this is following the input. That's the transient response. Okay. And then we also kind of paused here last time is dealing with causal system and the stability of the system. So the logic is this. If I have a causal system, my region of convergence is an exterior of a circle. Let me use my pen to see if I can do this. Okay, let me use this. So if I have a causal system, usually my system is causal. So the region of convergence, which is the good part, is the exterior of the circle. Okay? And we also proved the last time that the unit circle, which is z absolute value equal to 1, this is important because that's the only practical signal we are going to deal with. Later we will see that's actually corresponding to the Fourier transform. So if that's important, has physical meaning, that has to be in the region of convergence. So this unit circle, let me use another color. Unit circle should be in the region of convergence, so in the shaded region, right? This is 1, that's -1. This is j on this point, and then minus j at this point. So that's my unit circle. Now, again, this red circle is my Fourier transform is actually on this red circle. So that has some physical meaning. I want to make sure it's in the region convergence. Therefore, if it's stable, that means all the poles of my system, it can be a real pole, it can be some complex conjugate poles. Pole means that my system is divergent, right? It's just infinitely large output. And that has to be within this, actually the blue circle, which is, region of convergence, not region of convergence interior. And of course, strictly speaking, that should be within the red circle, which is the unit, the unit circle. So we have some conclusion draw from here with a lot of those logic discussions. We said can we see that? A causal LTI system, practical, it is stable, bounded input, bounded output, if and only if all the poles are inside the unit circle. So that's the kind of the criteria we look at for a good system, right? Compare with Laplace transform, we know all these Laplace transform is S-plane. All these poles should be in the negative part, in the left half side of S-plane, which is the real part of the poles are negative in Laplace domain. Okay, so that's what we have last time. So okay, this is too large. Okay, how about that? Can you see that? Okay, so let's finish that, give an example. I want you to spend a few minutes just to think about this problem. We have a LTI system. It is characterized by the system function or the system response, which is capital H. Hz is in this rational format. Okay, it's a polynomial divided by another polynomial. So I have done the partial fraction expansion for you. So actually the denominator, you can factorize that into two parts. So those are the two poles. Give me those two parts. And then the numerator, I can actually calculate it because it's a proper rational function. So all these fractional formats, they need to have a numerator has order strictly less than the denominator. So from the top line, the numerator has order 1, if in terms of z to the power -1. If you're not familiar with that, we have to change that everything to z as a function of z. So the numerator is order 1, denominator is order of 2, it's proper. And then go on to the second line. On each part, numerator is order of 0 with respect to a polynomial of z -1. The denominator is polynomial of order 1. So again, that's proper rational function. So we are good. I want you to specify the region of convergence of Hz and then determine the time domain impulse response, little hn, for the following conditions. There are 3 conditions. First, the system is stable. Second, the system is causal. Third, the system is anti-causal. Okay, I'll give you maybe 1 or 2 minutes to think about it. If you have a paper and pen, you can think about it. If later you are watching on a video record, you can fast forward this. All right. I think I can explain. Let's work on this together. Um, so first of all, what are the poles of the system? Anyone? Right. You can, or you can write in the chat if you like. The poles, oh, okay. Thank you. I think that's correlated in. Thank you. That's correct. So there are two poles, 3 and a 0.5. Very good. So let me draw the region of convergence, right? Well, with poles, then I have to draw the boundary of region of convergence. Let me share with my um, this screen. See if I can do this. Oh, that should be the same. Yeah, yeah. Can you see the whiteboard? Okay, so okay. So I have two poles. One is at 0.5, it's probably here, 0.5. Another is at 3. It's 1, 2, 3, somewhere here. It's 3. Right. I have two real poles. Two real poles. Now, these real poles are actually give me the boundary of the region of convergence. So I will have a circle here with radius of 0.5, another circle right here with radius of 3. It's large. So it's like this, right? And then these two poles, they cannot be in the region of convergence. So the region of convergence should be strictly greater than or less than, so exclude these 2 points. For example, if exterior of this circle of 3, it can be a region of convergence, right? So it was strictly larger than these, so exclude these 2 points. So let's look back into this problem. If the system is stable, so we have the solution here, the system has pole c equal to 0.5 and c equal to 3. If the system is stable, the region of convergence must include the unit circle. Okay, so here is system is stable. Well, the poles should be, but the poles should be within the unit circle. But I have a pole of 3, right? How do you deal with that? Well, if that is the case, then I need to make sure that the region of convergence is not it's really not the exterior of a circle. It's not causally this time. But the region convergence is more limited because I want to exclude both 0.5 and 3. And as we mentioned, the practical system is a system that has the unit circle because this is the circle that if later we know for Fourier transform, I am actually traveling along this circle. This is 1 minus 1j and minus j, unit circle. And that is the only z value make physical sense in my Fourier transform. So I need to make sure this part is safe. So I will put here inside. This is my region of convergence. Exclude these. Well, I cannot erase, but exclude them. So within these two circles, I'm using double. If this is my region of convergence, And then the unit circle are in the region of convergence. So that's good. I do have a stable system because I excluded all these two poles, 0.5 and 3. How? By doing this, right? If Z is within 0.5 and 3. And then I can do an inverse Z transform. So two different parts. The first part is actually causal, exterior of circle radius 0.5. The second part is anti-causal, that is internal of the circle radius 3. So I have generated this. This is my result for a stable system because I want to make sure region convergence contains unit circle, but it's non-causal. Second question is, if the system is causal, then the region convergence has to be exterior of the circle. So there's only one way I can exclude both points, which is the absolute value of Z greater than 3. And then you can generate this. Now, this is my causal system, but this system unstable because I do have my unit circle is not in the region of convergence. So in practice, I will not be able to implement that. Or in a way, the system will become output larger and larger, eventually blow up the system. Third problem, similarly, since the system is anti-causal, then the region convergence is strictly inside of a radius. So it has to be less than 0.5 in that way to exclude both poles. So we have this is anti-causal time domain signal. Again, that's unstable. Unstable because the unit circle is not in the region of convergence. Okay. So I think that's a good example to show us how to deal with inverse Z transform, considering the poles positions and the region of convergence. Okay. Okay, lastly, I just want to mention there is a process called the pole zero cancellation. Pole zero cancellation is, as we see, we can transfer the system function into the Z domain, capital HZ. We can also transform the input signal into the Z domain with capital XZ. And you multiply these together, give me YZ, right? Y is equal to the product of these two, is H times X. And by doing this product, what we can do is I can, using some smart input signal, I can cancel out your system poles. If the poles are outside in a circle, something that make my system unstable. So I can argue that my system cannot deal with all signals, but I can deal with a certain kind of signals, which you will have a 0 exactly on that pole, such that the pole is canceled out. Okay, so I can make some smart move on that. So this again, later we will show some interesting problem. Actually, I have a midterm exam on that. So how to design a signal that can cancel out an unwanted pole of your system. All right. So with that, let me get into some of the MATLAB part. Okay. So here is a MATLAB symbolic format. Hope it's not too small. You can actually check with a Z-transform using a very simple function in MATLAB called Z-trans or inverse Z-trans. It's very easy, but you need to install the symbolic format of MATLAB so it knows that keep n or z as a variable. So let's look at some of the examples. So if I want to compute a Z-transform of sine n, what I can do, excuse me, I define a symbol. You have to install the symbolic MATLAB toolbox. I define a symbol, it's called n. So I can put a function f is equal to sine n. Then I do Z transform on my function. Let's see what we have. Let me just copy this, paste it here. Go. So it gave me the answer. Very nice. It gave me the answer of Z transform in the Z domain. That's a function of Z, actually a function of Z. So it's given like this. It's a rational format. And well, I leave that for you. One of the things is that it doesn't show the regional convergence, right? So is that a regional convergence is by default, what should that be? It should probably give me a causal signal. So I'll leave that to you. I hope you can take some time. Just do a very simple help. In MATLAB, you type help Z-trans and you understand that. And then I can also compute the Z-transform. The second example is like exponential function, m plus n, m plus n. By default, the n is the time domain signal. And let me just first run this. N is the time domain signal. M is any variable. If you not define, it doesn't know. It just keep that, right? So it keep the variable m here, but give you the output variable as z. But he better understand n is the time domain. That's t. That's n. So it will do that. You can, by default, the output, the transformation variable is z. But you can define this as another transformation variable and just put it in the function like your function f. What is the output you want? You want to have a variable called y. You define the symbolic y. And let's do that. And that just gives you y, right? Instead of z, now it gives you y, right? And then lastly, you can define both the time domain variable and the z domain variable. So in this case, I have a function that I just wrote, I defined. I know now this m is my time domain signal. Y is my z domain, time domain variable. Y is the z domain variable. So if I run this, it will give me that. It will treat n as just an arbitrary variable. It's not time because you define m as time domain signal. And the output is y instead of z. So it gives you that. Okay. So isn't that nice, right? It's very nice. You can just check your result for Z transform. The only thing is that you need to pay attention to the regional convergence that I mentioned. The last part is showing you the inverse Z transform. Same thing. Well, okay, that can solve a lot of headache because I can check my partial fraction expansion as well. So the function is I Z trans of F. Same thing. I need to define a symbolic Z, which is Z domain. I define a function, capital F. This is a Z domain function, right? So I better put in a rational format. Make sure I will have a difference equation and give me constant coefficient as output. I will encourage you to try some other functions, some weird functions. Let's see what you get from inverse Z transform. So let me copy this and run that. So it will give me a time domain function, which is 2 to the power n plus 2 to the n times n minus 1. So this is what I have for the time domain signal. Right? Actually, I have a double pole here. This is z equal to 2 have double pole. So you have 2. This is one root is 2. The other root is 2, but you need to multiply by n minus 1, by n minus 1. Well, you have a delay term there. You have delay term. Actually, 2 times z. If you translate everything, well, in MATLAB, it's z, but if you translate everything to z to the minus 1, you'll find out that's a delay term. Okay, so the next, if I have a variable a defined, so here, let me copy that. So you have a defined, well, it will take this a as the time domain signal. Okay. Oh, the excuse me. This is just one variable. If I'm not defining in my inverse Z transform, so a is just one variable. By default, it takes z as the transformation domain variable, take n as the time domain variable. You haven't seen anything in the inverse Z transform, so we'll take that. If you have another variable defined symbolic variable a, it will just keep that. So the answer, I run it, the answer is canonical delta n minus 1, 0 over a. Canonical delta is our delta function in the discretized domain. So it's called canonical delta. And you can neglect this z. Actually, there's another variable if you check with the definition. But it's canonical delta n minus 1, right? Canonical delta. Why is that? Well, what do we have here? We have here function is 1. 1 over a. A is another variable, so I just keep that variable. Nothing to do with time. No. What is that? This is in the denominator. That's z to the minus 1. So that's just one delay, right? Delay unit z minus 1. And I'm actually doing an inverse Z transform on 1 or 1 over a. Therefore, of course, my inverse Z transform is delta function. That's a canonical delta over a. A is just that variable. And then I have this delay. So it's n minus 1. In the time unit, that's n minus 1. So we have that. All right, so I've checked my result using inverse Z transform. What I expected is correct. So if you have this M inside IC trans, it will take that as a time domain variable. So if I running this, copy this, and then it will say, okay, you put an M here. So I know M is your time variable. So instead of N, you're doing an M here. And lastly, I can also define here, which is A. Now A is my transformation domain variable instead of Z. M is my time domain variable. So it will give me this. Well, M is used as time domain variable, but you said A is the Z transform domain variable. So it will treat this Z as a arbitrary variable. Just keep it here. So it's just a way you have to define a function here. You put a input variable, which is the transformation. In my case, is the transformation domain variable or inverse. And then the output, the time domain variable, default is n. Now I put it in. Okay. So, all right. So I use these examples as conclusion for Z transform. Again, some of the numerical examples I will do next time when I get back to beta. I will work that on board. All right. Are there any questions so far on this part? Okay, very good. Let me share this again. So if we don't have any questions, I will continue with the next chapter. Some of the concepts I'm going to do it today. Again, we will leave all these numerical examples later. So now we have a very strong tool called Z-transform. Z-transform in the transformation domain. And we know one of the reason is because in the transformation domain, convolution for system becomes a product, and that's it. And it's easy for me to play with the signal input output, and I can do division, find the system itself, HM. But what is the physical meaning behind that? Z transform is a transformation mathematics. It actually has a special case, which is the frequency in the Fourier domain. So today we're going to look into a new chapter called the Fourier analysis of signals, a frequency analysis of signals, and using Fourier transforms, a special case of Z transform. So, excuse me. Let me double check on that. Yeah. So my connections are coming back right here. Yeah. So, yeah. Okay. Um, No, here. Yeah, so this is the right page. I can. All right. So for this chapter, so the outline is I'm going to go through the frequency analysis of continuous time signal, then including the Fourier series of continuous time periodic signal, power density spectrum, the Fourier transform for continuous time aperiodic signal, energy density spectrum of aperiodic signals. So different categories, we are getting the details of the Fourier domain. We will see that. And then we will have a frequency analysis of discrete time signals. The previous part, the top part is continuous time signals. We kind of review what you have already learned in signal and system. Then the next part, I'm going to dig into the digital systems. And digitized, not really digitized, it's digital in the time domain. So I call that discrete time signal. But in the frequency domain, let's just, in the amplitude domain, y-axis, let's just leave it as an unquantized, just arbitrary value. Okay. So throw out the equation first. And what we want to do, so we want to deal with a signal. Now this time is a continuous time signal, xt. I want to decompose that into a lot of sine waves, sinusoidals. We always do that, right? We decompose into harmonically related complex exponentials. So first, if xt is a periodic signal, if it's periodic, then I can decompose into a group of those exponential functions, which is sine wave. This is basically sine wave with frequency f naught times k. K we will mention is this index. That's why we call it harmonics. So we have a sine wave of frequency f naught, 2f naught, 3f naught, and a 0, minus f naught, minus 2f naught. All these are the sine waves that has a frequency with a fundamental frequency f0. Can call it harmonic related. And then we adding all these together with a weight on each sine waves of c sub k. So add them together. Okay. In this case, you will find out actually these sine waves, what I put in the box, these sine waves are actually discretized in frequency. So I have a 0. I have f0, which is the fundamental frequency. I have a 2f0 sine wave. This is a frequency domain, but weighted differently. This is weighted as C0. This guy is weighted as C1. This guy is weighted as C2. And add them together. Okay. What about a frequency component in here? Let's say half of f naught. In another word, I'm asking, why do I have discretized frequencies? It's exactly on 0 or minus f0, f0 to f0. This is because I have a periodic signal. I have a periodic signal. So we mentioned that in the almost beginning of the class. If I have something periodic in the time domain, in the transformation domain, in the frequency domain, it's discretized. So indeed, we have discretized with a fundamental frequency f naught. So from here to here. Now, how does that relate with periodic signal periodic? Well, actually 1 over f naught is my period of the signal, t sub p. This is the period of my periodic signal. Actually, the periodic signal is the original signal that Fourier himself dealt with at the very beginning. He is dealing with periodic signals and decompose into those harmonics. Okay, so if you understand that, then it's very easy to lay down. We memorize the Fourier transform very easy. So we have this, we call the synthetic equation. So you have an arbitrary signal, you decompose into a group of combinations, a group of harmonics. It's a linear combination of these harmonics. So for those coefficients C sub k, there is a way I can calculate. So these are the C sub k's. I have a way to calculate. Mathematically, I can solve for that. And C sub k is equal to this. It's 1 over Tp. Now, Tp, okay, actually, I wrote it here. Tp is directly related with my harmonic fundamental frequency, right? 1 over F naught is equal to Tp. And then I'm doing an integration over one period. I take my original signal, which is this signal, multiplied by exponential e to the minus j 2 pi f0t. Almost the same. The only thing is I have minus sign here. And then integration is over time, t. Okay. So if you look at this and this, this exponential is very similar. The only difference is in the power. One is positive, one is minus, is negative. We call this the analysis equation. Analysis equation is that I am going to take my time domain signal. I'm going to give you C sub k's. Now, what are C sub k's? C sub k's are this, right? C0, C1, C2, and it continues C3 and minus C1. It can be negative, it can be complex. So if you look at these C's, C's are a picture of the signal in the frequency domain, which is the frequency domain signal. So you really know, we know this is actually XF, but it's just discretized, right? This C sub k is really a function in the frequency domain. So you have a time domain signal, transfer that into a frequency domain signal, and that is the direct Fourier transform. Now, what about this synthesis equation? Well, you have a frequency domain signal. You want to get back to the time domain signal. So this will be an inverse Fourier transform. All right. So originally, Fourier again dealing with a periodic signal, but he is using cosine sines to write out the synthesis equation in this format. So everything is nice, everything is real. You don't have exponential. So you will have a DC part, which is A naught. And you have cosine, which is coefficient with A's, sine coefficient with B's, and you have a minus sign here. And this is the original Fourier transform formula. And later that actually after a few decades, another mathematician has come and using the exponential to replace everything. And it just becomes very tractable, mathematically tractable, and it looks beautiful. So, but here we know all these coefficients are related with the previous complex coefficient, A naught and C naught, A sub k, B sub k. It can be written in this format. And the C sub k, of course, you have the real part and the phase. C sub k is a complex coefficient. But today we all use the previous equations, so we introduce the complex notation. Okay. So before we move on with Fourier transform, we need to give out some of the conditions. These are the conditions called Dirichlet conditions that guarantee that xt and its Fourier series representation are equal at any value t. So we are just going to look at today, but later on we will assume by default these conditions are satisfied. So the first one is xt has a finite number of discontinuity in any period. In any period, I have discontinuities. My xt, you can discontinuous from here to here. That's fine. But as long as within a period, these discontinuities are finite, well, in practice, it's finite. Only some theoretical signals, you may have infinite many of these continuous, but we're not getting to that. So usually, all the practical system, this is satisfied. Xt contains a finite number of maxima and a minima during any period. Of course, for a practical system, you have a maximum, you have a minimum, and at these points, you have finite number of that because you're within one period. It's finite number. Again, for a practical system, this is satisfied. And the third one is xt is absolutely integrable in any period, which means I do have a signal that's integrable like this. So you may have some signals very weird, like from minus infinity to infinity. This, like this, those kind of signals, right? And again, those are not practical signals because in practical, xt is always, in a way, it's the value is finite. So again, in practice, this is also satisfied. Though these three conditions need to be satisfied in order for me to get a valid Fourier series expansion. You can actually verify that if you think about what we talk about a unit circle in the Z transform, if these conditions are satisfied, the unit circle should be converged. The points on the unit circle should be converged in the region of convergence. Okay. Let's look at a few of the definition of the signal, how to deal with that. One definition is called the power density spectrum. Power density spectrum is I'm looking at my signals, and in a way, I want to find out the distribution of the signal across different frequencies. I want to see how large is my frequency with oscillation of 2 hertz. How large in terms of power of my oscillation at 100 hertz of the signal. That actually gives me a lot of insight of the signal. Is this a high frequency signal, low frequency signal, and how can I play with it? How can I deal with it? So what we do is we take a periodic signal. It has a periodic signal has a finite average power, right? It's periodic, so you have the limited range of the signal, and it's satisfying the Dirichlet conditions, so the average power is finite. What we do is we do this to find the average power. We are doing integration of xt. Xt, absolute value squared. What is that? This is xt, if x is a complex signal, can be any complex signal, xt conjugate times xt, right? It's a little xt. So this part is, we call it instantaneous power of the signal, exactly on time t, instantaneous. And then I integrate it over one period of tp over dt. That is the energy. That is energy of a signal within that period, divided by the time spent tp, and then it becomes average power. So this is indeed the power of the signal. So we have that after calculations. This is true from the absolute value square. Then I am using one of the analysis equation to replace my little xt. This is the previous equation, which is I using the analysis equation because I have a complex sign here. So make sure that I have a complex sign here for the complex coefficient and a complex sign here for the exponential. So originally should be positive to the power. Now it becomes minus j2 pi kf naught t. So I put it here. This is really, it's coming from this signal. And then using my Fourier transform equation or the analysis equation, get that. And then what we do, I swamp the order of this integration and a summation, because integration and a summation both are linear operations. So I go through a summation first, operator, and then I go through this integrator. It's also a linear operation. I can swamp the order of these two boxes. So what I am doing here, I'm doing the integration first with respect to xt. Integration has a integral variable t, therefore I have a t here. So this part should be inside my integration, e to the minus j 2 pi k f naught t dt. Okay. Once I do this integration, that has nothing to do with t again. And 1 over tp, this is a constant, so it doesn't matter. I can put this inside here and make this entire thing in my bracket. C sub k has nothing to do with t, so I pull this out of my integration. Then I will sum over k, because this is a k here, that's a k here. Then I do my summation, right? So I exchange the order of these two linear operations. And then if you look at this bracket, that's very nice. This is my my previous examples calculating C sub k's. C sub k's. This is actually the forward for a transform. Forward, we call this synthetic, the analysis equation. And so we end up with C sub k conjugate times C sub k. So we have a C sub k absolute value squared like this. Now that is my periodic signal average power. So if you look at C sub k's in this plot on the right, a frequency domain plot, I can plot this out because C sub k squared is a real number. It's not complex. So I can easily plot here. If you're adding all these together, that will give you the average power of your periodic signal. So what about each one of those? Each one of those actually is the power distribution. Tell you how strong that is on particular frequency. For example, in F naught, there will be C0 absolute value squared here. Right? And so on and so forth. This is the distribution. So we have that, we call that the spectrum. Okay. Last slides for today. So if I am going that from a periodic signal to an aperiodic signal, the previous I'm discussing everything for periodic signal. Going to an arbitrary aperiodic signal, what can we do? Well, you can make the period T sub p approaching infinity. And then we can derive the equation. For example, let's try it. We have a periodic signal called X sub p, again, with a period of T sub p. It's just that I'm going to take the limit p approaching infinity. That will be my aperiodic signal. So with X sub p, I know this is, well, if you think that's a periodic signal, so I can use the Fourier series expansion like this. Right? This is what we have previous slides. And then I have a fundamental frequency T F naught is equal to 1 over T sub p. Okay. I also have my coefficient C sub k can be calculated like this. So you are doing integration over one period. Can be from 0 to T sub p, or I can also use that, just make it symmetric. From minus TP over 2 to positive TP over 2, but that's integration over one period. And I put in that divided by T sub p, and that will give me C sub k. Okay. So I'm going to do a few of the tricks here. So first of all, I will do with this integration limit. So if it's minus T sub p over 2, but you just tell me that T sub p is infinity. T sub p is infinity. So I can change that in minus infinity to infinity. Then I keep the rest of here. I call the entire thing of this integration, I call that capital XF. F is, or F I actually leave that as a question. F something related with that, right? Something with that. So if you think about this discretization in frequency domain, 0, F0, and 2F0, this discretization in frequency domain. Now with this condition, what about the distance between here and here? What about F naught? F naught is 1 over T sub p. It will approaching 0, but it's not exactly 0. We can mathematically, we can say that's an infinitesimally small number, small quantity, right? So this gap, eventually this gap here, this gap will close. So if you think of all these discretized signals, eventually if the gap is closing, so you will have a continuous function in the frequency domain as well. And that is exactly what we have here. XF, that is my continuous function as a function of f in the frequency domain. So I will leave you a few questions and think about it, then I'll continue next time. So what do you do with this, right? K times f naught. What are you going to do with that? This is K. The second question is, what do I do with this T sub P? T sub P becomes infinitely large. Wouldn't that be you divide by T sub P, so the entire thing goes to zero, right? How can I mathematically deal with that 1 over T sub P? It's not zero, it's very small. But how can I deal with that? And then replace with some mathematical variables so I can derive the famous Fourier transform. And that we will discuss next time. Okay. All right. Are there any questions so far? Okay, very good. Very good. Thank you again for your patience. I really appreciate all you are here online with me. And I will record this video and post it online as what I did. You all have a great day. I will talk to you next time. If you have questions, just send me emails. Bye bye, dear class.